What's up, everybody? Welcome to Air Science. Take 3. We're going to see if we can get this metamorphic thing to work this time. So let's open the door with this diagram, which you should have done on the first day of rocks, and then afterwards you've already done igneous and you've already done sedimentary. That should all be done before you get to metamorphic here. Don't skip around. It's not really going to help. The reason I want to pop this back up is to think about the pressure it takes to form a sedimentary rock. We did mention pressure there, and we'll be talking more about pressure today. But a great deal more pressure is needed when we start talking about metamorphic rocks. When you get down there fairly deep in the earth, it can happen near the surface sometimes too. We'll talk about that. But the pressure we consider today is way higher than what it takes to lithify a sedimentary rock. So what are these metamorphic rocks? They're basically, you take any rock, any one of the three, a sedimentary, an igneous, or even another metamorphic, and you change it due to heat and or pressure. Now you might say, well, the rock cycle is always like things are changing, right? Yeah, sedimentary is like, it gets broken down into sediments. That's the changes. It breaks down in little bits, and those little bits aggregate back into sedimentary rock. And yeah, igneous like melts. But the difference here is that the change is that you take that individual rock itself and put it under enough heat and pressure to take it and actually alter the minerals that are within it. All right. The term a metamorphosis you've probably heard before, and I bet you I'm going to misspell it, but we'll let Google figure it out here. If you've seen Gremlins, which if not, I recommend, it goes from the cute fuzzy gremlin, and if you accidentally feed it after midnight, it turns into this evil slimy gremlin, right? It's a metamorphisis. I bet you that's it. Yeah, not bad. Oh, there we go. Metamorphosis. A change. It's just a change, right? Caterpillar to butterfly, that kind of situation. It's a change. This is a physical change in the rock due to heat and pressure. All right. This crazy graph. What are we looking at here? The idea is that we're going to look at this graphically, but also in terms of where this happens within the earth. So think of it like an XY axis graph, like you've done many of, and like you do in your math classes. X-axis is temperature, increasing as we go to the right. Now our Y-axis, instead of going up, which you're probably used to, on this diagram, it goes down, which is meant to, it's really no different, right? But it just shows us that as you go deeper in the earth, here's what happens. And I do a very good job of spacing those out, but that's all right. So as you go from 10 to 20 to 30 kilometers deep into the planet, what happens? And as you do that, over here it says pressure in a unit that I can't make out at all. No big deal. Don't worry about any of these numbers. You're not going to have to quote any of these numbers at any point. But the idea being that as you go deeper within the earth, simultaneously, the pressure is increasing. Okay? So we're going to do some light drawing on this. We have another one of these to do down below, or we'll get a little bit more complicated, but don't worry about it. Stick with me. You're going to be fine. So I'm going to put a little area in here. This area in here I labeled with an S. That would be where you're forming sedimentary rocks. A little bit of pressure, maybe a little bit of heat as you get down in the earth. Not too serious, though. Let's go all the way to the other end of the spectrum. If you go past this dotted line right here, which is labeled, this is the melting point. Go past that, you've got melts. Melt, we're not talking about metamorphic rocks anymore. Now you've entered the realm of magma, igneous rocks, all of that, right? So this big area in here will be where we form metamorphic rock. This little funny area right here. I'm gonna go smaller. Don't worry about it. It's what happened. Nothing happens here. This doesn't exist. Conditions don't exist. You can't get this deep within the earth without the pressure also increasing. There's nowhere where that happens. It's hot down there. So this is just like graphically, this doesn't happen. Like the graph should just have that curved line, but that would be awkward looking. So Nothing happens there. Don't worry about it. Scribble it out. Who cares? All right. So a little bit of heat and pressure, maybe you can turn sediments to sedimentary rock. Too much heat and pressure, you melt it and you get igneous rock. Three Little Bears idea, just right, which is a pretty big area. You can form metamorphic rock. When you get to chemistry, if this is bugging anybody, you're going to see that melting points are dependent on pressure. So are boiling points. So that's why the melting point isn't just 900 degrees. It's 900 degrees at surface conditions for some magmas. But as you go deeper and there's more pressure on it, these things can change. So don't panic about that again either. Let's keep it simple. I'm already rambling too much. All right, so we're going to deal with two main types of metamorphism, regional and contact. And when we get to the reference table, you're going to see those words pop up here. Type of metamorphism, regional contact. Big goal here, what we're trying to do is just learn to identify these rocks. And then same as usual, you'll get your rock lab, except I opened up the igneous one. I'll have to change that. And yeah, you'll do great. So what are the two types? Regional is when a large area put under heat and pressure. We're going to draw this right here. So if this is like, what is this guy talking about? Just chill for a sec. We'll cover it. Contact is going to be generally a small area, but under heat only. That pressure doesn't really come into play a ton with contact metamorphism. All right, so what are these situations? We're going to draw them right here. Don't be intimidated. You know, I'm not very good at drawing either. We'll keep it simple. So I'm going to draw a good old version of a volcano. And like we did on that previous lesson, the first lesson in rocks, we'll have it fed by some plumbing, for lack of a better word, from down here. Melted rock, magma, hot, right? This rock over here on either side is cool enough that it's not melted. It's solid rock. So here is what might happen is that as this magma is working its way towards the surface and it's hot, what about the rock that it comes into contact with? It can alter it a bit. Will some melt? Yeah, some will melt and get into that magma, come squirting out of the volcano. That happens. But again, that's an igneous rock. What about the rock that's close enough to that it gets so hot that it changes the mineral structure of the rock? Not way over here where it stays cool enough where it just does its thing, but right next to it. Now, this is going to seem weird, but I'd like you to try to do it. There's a kind of universally accepted symbol for this contact metamorphism where you draw these little squigglies on there. It's not meant to represent what it actually looks like. This is like a commonly used symbol in these cross sections. Because it takes a minute. Press pause if you have to. A commonly used symbol in these cross sections to indicate that contact metamorphism has taken place. So again, since this magma right here is melt, it's hot. Duh. This right here, the edges of it get altered a little bit, go through contact metamorphism. So what the squiggles mean, they equal contact metamorphism. Now, today, we'll just say, great, cool. There's contact metamorphic rocks. That's a thing. Excuse me. When we get to Earth's history, the last unit we're going to do this year, and we start figuring out how do we know how old the rock is? How do we know which things have happened first? What is the sequence of events that led to an area looking the way it does? This contact metamorphism is going to be huge. Okay, so that's what it is, right? We'll functionally use it later in the year. Today we'll just say, okay, there are contact metamorphic rocks. They are this on the reference table, blah, 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 and you'll be fine. It's not really going to be a big deal. All right, let's try to quickly do, I keep saying quickly, I know I'm going long here. Keep it up, folks. let's try to do regional metamorphism, which, as I said above, is going to be a large area. This is a small area, just adjacent to melted rock, to magma. This can be like a whole entire area. So, a long time ago, before there were humans to stick flags in the ground and say that this is something like India, this is something like Asia, this is something like North America. Pre-human, India was its own separate island floating out there in the Atlantic Ocean. Now I'm doing this in cross section. If that's hard to see, what I'm going to do is draw a little person right here, and this person is not to scale. This person would be preposterously oversized, way, like not even Godzilla big. Like Godzilla be the size of their foot. This is a huge person. This is the thickness of the continental crusts, and then down here, when we do tectonics, we'll have to figure out what's going on. Come up with better names for it, but for today, let's just say that it's the magma down there. Okay, so that's the cross section. Looking at the planet from the side, India is its own separate continent, and it's moving that way. This is jumping forward into tectonics a little bit, but it's just to give us our setting for regional metamorphism. And while India was plowing northward through what would one day be called the Indian Ocean, Asia was sitting right there. Like, we oftentimes do this. Effectively, they're moving towards each other. And it went from separate island, boom, the two ram into each other. And hopefully not in person, but if you've ever seen car wreck on TV or something, when two car hoods hit each other, they like crumple all up and mash all up. That's has been happening, and has built the largest mountain range we currently have on the planet, the Himalayan mountain range, containing Mount Everest and others. And mountain ranges not only go up into the sky, but they also have deep roots like that to maintain like an isostatic balance in this mushy magma. If you just build it high, it would just sink back down in, right? So these are the thickest parts of the crust. And now with the momentum of two continents coming at each other, it's a lot of heat and pressure down here. So this is what we'll say, like, this is a very rough estimate. I'd rather do this in red or something. This is a rough estimate, but let's say maybe even a little higher than that. But this whole area down here, which is a substantial amount of earth, a substantial amount of rock, will be undergoing regional metamorphism. All right, which is one of the reasons why metamorphic rocks are cool, because this is our snapshot today, but we have regional metamorphic rock exposed, like in the Adirondacks, right? Thousand Islands, you can see it too. So what's the deal? How did that happen? So what you're getting to see with that rock is that was a place where way back in Earth's history, continents went through a collision. And then as that all calmed down and it went through years and years and years of weathering and erosion, the whole entire top got stripped off, leaving us to see what has gone down way down deep within Earth's crust, which is kind of neat to me. Okay. Let's check this out quick. We're going to do this. It's going to be a little bit more complicated. I'm sorry. I know I'm going long. But my goal here is that the lab is going to be the easiest of the rock labs, because I'm going to hook you up with so much through these notes that by the time we jump into that lab, it's going to be, you fly right through it. All you got to do is really use the reference tables. Heat and pressure will compress the rock so that their density increases and their hardness increases. You're familiar with this if you've ever made a snowball. Take a couple hand scoops of snow. It's low density. So what do? You mush it. You put it under pressure, and you increase the density and the hardness so you can whip it at somebody. So that's going to be part of what we talk about here. So let's just chuck in real quick from above. This is melts. This just is not a thing that exists. I'm just going to do like a circle with a cross through it, right? And this is sedimentary. That's not really the stuff we have to concern ourselves with today. Graphically, what goes on, I'll switch to bluish purple here. We'll throw another little area up here and say that this is really cranking up the heat, but not really cranking up the pressure too much. What type of metamorphism does that sound like from right above? I wish I could ask, but we're here on YouTube. There's our contact metamorphism. There's really another one that happens like right along this line. I'm going to just ignore it so that we don't go too long here. But should you become a geologist, you can learn about subduction metamorphism too, when a plate gets sucked right down in. Close enough for today. So what we're going to have through here then is a series of increasing heat and pressure, increasing heat and pressure, increasing heat and pressure. I'd also like to note in the reference tables, we've got a whole section, the whole top here is regional metamorphism with heat and pressure increasing, 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 increasing. And you get these 4 rocks: slate, phyllite, schist, and gneiss. Your lab is going to have those 4 rocks in order, and it's going to say increasing heat and pressure. So you're really going to get the answers ahead of time, meaning the lab is more about like, okay, look at the picture of the rock, check something out, but really use the reference tables to help you fill out the whole lab. So slate, phyllite, schist, gneiss all form as the pressure goes up, 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 up. So what we can really do up here is to say that slate forms, and then the heat and pressure increases, and phyllite forms, and then the heat and pressure increases. Schist forms, and finally gneiss. So you get to experience that. And that's what the lab is going to do, is bring you through, here's what this rock is. Now crank up the heat and pressure. Boom, next rock. Crank up the heat and pressure. Next rock. Crank up the heat and pressure. Next rock. I think there's 6, 7, 8, 9. In fact, I should open up the lab. I'll pause it here so I don't kind of fiddle around on camera. So yeah, when you do it, and I'll do a separate video for the lab. I tried to combine both in yesterday's failed video, and it got too long. But for 6 to 9, the heat and pressure increases 6, 7, 8, 9. And that's what the lab will do for you. 6, 7, 8, 9. There's your answers. Just work backwards. All right. To identify metamorphic rocks, once again, we will have to pay attention to the rock's texture. Now, if I were to ask you right now today, what am I talking about when I say a rock's texture? And if you are in your head saying, well, that's how the rock feels, if it's rough or smooth, unfortunately, you're wrong. What the rock's texture refers to is the size and shape of grains in the rock. Take a piece of gneiss, granite gneiss. If you were to, there's pieces of it all over the place. You can go to the beach and find them. If I were to take it and hit it with a rock hammer a bunch of times, I'd have a whole bunch of jagged pieces that would feel rough on your skin. If we let those roll around on the beach, they'd get all round and smooth from abrasion. But it's still granite gneiss with the same texture. So texture is not how it feels. I wish they just had a different word entirely for this, so that we didn't have to have this. I have to have this discussion every year. It just means a different thing to a geologist. The geologist says texture is this, the size and shape of the grains in the rock. That's what you'll be looking for. It's what you've already been looking for in the other 2 rock labs. So nothing too major there. So we'll see 2 major groups of textures. To identify these rocks, we need to see the difference. So foliated, that crazy word, means that there's some type of mineral alignments. Then one type of foliation is that it's banded, which means that it has big, bold stripes. So if in any way you can see minerals line up, it's a foliated rock. Now, in your lab, since you're not going to be able to pick up the actual rocks themselves, like that one, okay, that's banding. That's the big, bold stripes. You can see alignments. 6, 7, 8, 9 are all foliated, but that one doesn't really look like it. If you can pick it up and look at it from the side and we can look at certain things, it's much easier. But since almost everybody's not here this year, and we're doing this with these documents instead, that's why I'm helping out so much here, because this would be really hard to do on your own. And then guess what? This one up here is not foliated, and even though it looks like it. So the nature of foliation is kind of tricky to understand. Non-foliated would be that there are no mineral alignments. Now, the reference table is here to help. Again, this is like my most 100able test in a normal year because, and if you can go back to that assignment where I made you go and just like find words, find vocab words, like you had foliated was one of them. Once you found foliated, you said, oh, that's metamorphic. That's really the key to making it through this test. There's not a ton of memorization. I know this seems like intimidating and look at this crazy graph and blah, blah, blah. There's just not a ton of memorization. It's really everything is sitting here for you. So if in your head it can go off foliated, I know that's on, even if you just say, I know that's in the reference tables, open up the reference tables, be patient until you find it, and then look at the rest of the question. What's the rest of the question asking? Does it only have this in it? Then it's this, and they'll be easy. The trick is opening the table and finding it. All the people that'll just won't even open the table. They're like, oh man, I think Mr. F talked about this. I should have memorized this. No, you don't have to memorize any of this. You just got to be able to use this table. Okay. So let's talk about how this is broken down. Then I'll quit, and we'll switch to the lab. So we've got foliated, which generically means that there are mineral alignments, and some of those mineral alignments are so bold that they're banding. Remember, those are the stripes. Or we've got non-foliated. You can go by grain size. Again, in the lab, I'm going to help you out. These comments, steal them for the lab because it's not easy. Like, it's not easy at anybody's level, let alone high school students, let alone high school students that are trying to do this remotely, to like look at this and be able to describe this in a meaningful way that's correct and like geologically accurate. It's not easy. So I'm saying that's why I'm having us work a little bit backwards. So use that stars not just for that one. That stars for like all of these. Use those comments to help on the lab. They can really hook you up when it comes to making observations that may feel hard. Yeah, composition is on the lab. If you do that, so slate's an easy one. Slate's just got mica. These three, okay, it's a little bit more writing: mica, quartz, feldspar, amphibole, garnet, and pyroxene. Those are all the minerals that are in that may be in those rocks. Compositions down here are a little easier. Coal is made of carbon. Quartzite's made of quartz. Marble's got calcite. If you remember, calcite bubbles in acid. That could possibly come up too. We'll continue to talk about that. Type of metamorphism will be on the lab. Some are regional, some are contact, some are both. So that's it, really. Like if you can work that table a little bit, you're going to be in good shape. Check these out if you have a minute. I may make it an assignment towards the end to work on some of these, but I think for now it's just good practice. It really is just like being comfortable, being familiar with this table, and you're going to do great. All right. I'll switch to a different video for the lab so that this one doesn't get too drawn out and we can take a break. Keep it up, folks. You're rocking it. We'll talk to you soon.